In this video, we're going to learn about probability. This is 0026 in terms of, which strand are we covering on the MTEL. And let's, go right to it. So now, to begin, we're going to be looking at the probability of certain types of events. There are two types of events. Namely, there are independent events and dependent events. And if you really think about what those words mean, you can kind of figure out what exactly we're talking about here. So independent events are events that don't depend on each other. Now, that's not a great definition. So the definition we will use is, for independent events, they are statistically unrelated. They have nothing to do with each other. They do not impact each other in any way. So they are statistically unrelated. So if you know one event's outcome, it will have no effect on the probability of the second event. So here's like a great example. Like if it is raining and you flip a coin, those two things are said to be independent. It doesn't matter if it's raining or not. That's not going to give me more, let's say, heads or tails. Dependent events are events that are affected by each other. So, for instance, the probability that someone is wearing a dress and the probability that someone is a woman, those two things are dependent. And granted, men can wear kilts, but they are going to be affected or related by each other a great deal. If the person is wearing a dress, it's more statistically likely that they are a woman. So those two events are dependent on each other. So if you know that the person is a woman or not, that will affect the probability of them wearing a dress. So those are dependent. So independent, rain and flipping a coin, those are not related. But if you're looking at the probability of someone being a woman and the probability of someone wearing a dress, there will be some sort of overlap, or those events are affected or depend on each other. So we're going to kind of run through these situations, and I'm going to put a D for dependent or an I for independent. What is the probability that I draw a card from a deck, then replace it and draw a second card? What is the probability that both cards are a king? Well, since I'm replacing the card in the deck, these two situations are said to be independent. Doesn't matter if I drew a king or not the first time. I'm putting I'm putting the card that I picked back in the deck, and then I'm repicking. What I did previously has no effect on the next thing. So the key is that we are replacing, so these events are independent. Now what if I pick two tiles from a bag of Scrabble tiles, and I'm looking for the probability that both tiles are an E? Well, these two situations are dependent because the first tile being an E or not, it changes the probability of the second tile being an E. Because I want to say, I think there's 100 tiles in Scrabble, there's 13 E's, so if you pick an E on that first thing, there's a probability, let's say, 13 out of 100 that you're going to pick an E, but then once that's out of the bag and you're not going to replace it, then there's only 12 E's out of the 99 remaining tiles, so those two situations are dependent. This next situation is independent. If you roll two die, the probability that the two dice, the probability that the first die is a 5 and the second is a 4, those are independent. One die doesn't know what the other die is doing, so they have no effect on each other. So those are independent events. Again, we have independent events right here. If I flip a coin and roll a die, they don't know about each other. They have no effect on each other. Here is the situation where things are dependent. If you have 6 red M&Ms in a bag of 25, probability that first pick and eat a red, and then pick and eat a non-red, those two things are going to affect each other. That's just like the picking of the letter E in the Scrabble bag. If you're not replacing it, you're really going to affect how many M&Ms are left and how many are red and how many are non-red. Okay, so that's a dependent event. So here's like the formula for probability of an event. We'll write that as P event. So that event might say, let's say, getting a heads. So we might say P heads. That would be equal to, how do we determine this probability? Well, our denominator is going to be the total possible number of outcomes. And let's say we kind of think about this, flipping example. Well, the total possible number of outcomes, there are two possible outcomes if I flip the coin. The coin will either be heads or tails. And now the numerator, let's say, again, if I was looking for the example, P that I get a heads, the probability that I get a head when I flip a coin. The numerator will be the number of successful outcomes. So if I want to know if I'm going to flip a heads or not, there's only going to be one successful outcome out of a possible two. So that's how we get the probability. By the way, probabilities are always between 0 and 1. If something has a probability of 1, it is going to happen. If something has a probability of 0, it will never happen. And if the probability is somewhere in between, it will happen occasionally, based on whatever the probability is, ranging between 0 and 1. All right, so before we kind of go through this slide, let's just look at two separate events. Let's say I want to know the probability of rolling a 3, and I want to know the probability of flipping a head. So I've got my die. There are 6 possible options. I'm using my 6-sided die. I'm not playing Dungeons & Dragons. And there's only one winner. That winner would be if I rolled a 3. That's my success. So the probability of rolling a 3 is 1/6. If I also had a coin, the probability of flipping the coin and getting a head is 1/2. Well, since these two events are independent, we can actually multiply these two probabilities together. If someone said, what's the probability of rolling a 3 and getting a head? So we would say, okay, since these are independent events, we may take the 1/6. That's the probability of rolling a 3, and the probability of getting a head is 1/2. We would have our probability of 1/12. Again, I can't stress this enough, the only reason why you're allowed to multiply these two probabilities together is that they are independent events. So you can also use this idea. So the big idea, the multiplication rule, you could also use this idea on, let's say, another example of independent events. What's the probability of rolling, I don't know, 4 5s in a row? Every time you roll a die, you have an independent event. So the probability of rolling 1 5 is 1/6. Probability of rolling another 5 is 1/6, another 5 is 1/6, and another 5 is 1/6. So we will have 1/6 to the 4th, whatever the heck that is. That would be the probability of rolling 4 5s in a row. And again, we're allowed to multiply them together because each of these events is independent of every other event. So that multiplication rule is quite important. So now we're going to get into some interesting examples. What's the probability of a mother having 5 daughters and no sons? Well, the probability of having one girl is 1 out of 2. All right. So now what's the probability of having 5 daughters in a row, no sons? Well, that would be 1/2 times 1/2 times 1/2 times 1/2 times 1/2. And we're using that multiplication rule because I think it's fair to argue that these are each independent events. So there's a 1 in 2 to the 5th is 32. There's a 1 in 32 chance of having 5 girls in a row. That would be a real adventure having 5 kids, no matter if they were boys or girls. Okay, so that's the probability, and we can multiply those independent events together to get that. What's the probability of rolling a 6 on a die, then flipping 2 heads in a row? Well, the probability of rolling a 6 on a die is 1 out of 6, and then flipping a head is 1 out of 2, and then doing that again is 1 out of 2. These are all independent events. So our probability is 1 in 24, or 1/24. Mike makes 90% of his free throws in a game. What is the probability that he will miss 2 free throws in a row? Well, the probability of him making a free throw is 9 out of 10, or 90 out of 100. The probability of him missing, is 0.1, because the probability of him making it is 90%, otherwise known as 0.9. And notice how those two probabilities, you either miss it or you make it, they have to add to 1. So here's the probability of him missing it once, and we can actually multiply those two things together. So the probability of missing twice in a row, that would be 0.1 times 0.1, which is 0.01. And it might actually be better to use fractions. The probability of him missing is 1/10. And if he's missing twice in a row, we can use the multiplication property, multiply them together. 1/10 times 1/10 is 1/100th, otherwise known as 0.01, which is our final answer here. All right, very good. So here we get into some interesting stuff. Here's conditional probability. Conditional probability is finding the probability of an event occurring when another event is known to occur. So that word that they use a lot is given. So this is like that key word, given. So let's kind of rock out with these conditional probabilities. And you might find these a little bit weird, but we can make it work here. All right. So simple examples. The probability of rolling a 6 on a die is 1 out of 6. That's fine. That's not that interesting. But the probability of rolling a 6 on a die, given, there's your conditional probability, given that you have rolled an even number, is 1/3. So you have to think of it like this. Your denominator, there are only 3 events here. They're saying that you rolled an even number. There's only 3 options. You could have rolled a 2, a 4, or a 6. Those are the possible events or outcomes. And the one that we're looking for is that you roll a 6. That is one of the possible 3 even numbers that you were given that you rolled. So this is a perfect conditional probability question. The probability is 1/3. The probability isn't 1/6 because we were given our probability sample space only has even numbers. What about this last one? Assuming you have rolled an odd number on a die, the probability you rolled a 6 is 0. So you might think of it, well, rolling an odd number, there's 3 odd numbers if you rolled a die, namely 1, 3, and 5. Out of that sample space, could you have ever rolled a 0? No. And you could have just said right away, the only numbers you can roll in the whole realm of die is 1, 2, 3, 4, 5, or 6, so you could never roll a 0. So that probability is 0. That will never, ever, ever, ever happen. Now we'll get into some more interesting examples on the next section. So these problems are a lot of fun. Let's go for them. All right, so assuming you have flipped 15 heads in a row, what is the probability that your next flip will result in a head? Well, the probability of flipping a head is 1/2. And since each of these events are independent, it does not matter how many heads you flip before. And I think that this kind of speaks to something. I think it's called like the gambler's fallacy or whatever. People are like, 15 heads have come up. I'm going to bet tails because tails are due. Or I'm going to bet heads because, so many heads have happened in a row, it's going to keep happening. No, the probability is still 1/2 because these are independent events. All right, so you roll 2 dice. How about this next one? What is the probability you roll 2 5s? Well, on the first die, the probability of rolling a 5 is 1 out of 6. On the second die, the probability of rolling a 5 is 1 out of 6. These are independent events, so we can multiply them together. The probability of 2 4s is going to be 1/36. There's no conditional probability here. No, nothing like that. However, there's that word given in our next example. You roll 2 dice. What is the probability you roll 2 5s given that your first roll is a 5? So if we know that our first roll is a 5, all we have to really think about is the second roll. The second roll, rolling a 5, is 1 in 6. If we're already given that the first one is a 5, we don't, that's guaranteed. That's 100% clear that that first one is a 5. So the probability of rolling the second 5, given that the first one is a 5, is just going to be 1/6. You already know the first is a 5, so the second 5, the probability is just getting it is just 1 in 6. So here's that conditional probability that you have to reason your way through. All right, now we're getting to the fun stuff. Okay, so combinations. Combinations are when you're choosing things and order doesn't matter. A permutation is when you're picking things and order does matter. So here, for permutations, order matters. For combinations, order doesn't matter. So let's look at an example. Let's say I had this set. I had A's, B's, I had A, B, C, and D. I had these 4 letters. If I were to just choose, let's say, 2 letters, how many combinations are there? Well, A could go with B, A could go with C, A could go with D. B could go with C, B could go with D, or C could go with D. These are the 6 combinations of 2-letter pairings that I can make. And to be clear why this is a combination and why order doesn't matter is AC is the same as CA. All we were saying is if we just chose 2 letters, it doesn't matter what order. So these are the only 6 examples I have here. So this is just choosing 2 letters and looking at the pairings. So keep in mind, in this situation, we're saying if I pick A and C, that's the same thing as if I had C and A. Why? Because for both of them, order doesn't matter. I have a C and an A, so we're not going to double count them. There are only 6 different ways to do this. Okay? But if we took this same example and order did matter, and we were thinking about how many different 2-letter permutations or how many different, let's call them words. So we can think of it as 2-letter pairings, and we would call them words, meaning we're going to read from left to right. Well, then we would have AB, AC, AD. Now those are what we're going to call, quote-unquote, words. But we could also have the reverse of that, BA, and we could have CA, and we could have DA. Those would be considered different words because order matters because we're reading from left to right. And then we could have BC, or we could have CB. Those are different. And we could have BD, or we could have DB. We could have CD, compact disc, or we could have DC, the District of Columbia. So now there are 12 ways to do this, because even though we have the same set of numbers, we have different parameters now. Order matters, and AB is not the same as BA, because these are considered different words if you read them from left to right. And I know they're not really words, that's why I put them in quotes, but you get what I mean. So another thing to realize from the last example, in one of the situations we had 6 options when order didn't matter, and we had 12 when order did matter. That was just a perfect coincidence that one of them was double the other. So I just want you to be aware of that. So which would be better, a combination where order doesn't matter or a permutation where order does matter? That's the rules we're going to apply to each of these situations. Now, you select 9 of 15 people to be on a jury. That is a combination. Why? Well, you're either on the jury or you're not. It doesn't matter if you're picked as the 9th juror or the 1st juror. You're either on or you're not, so order doesn't matter. Now, here, if you get 1st place out of the 20 people in your race, that's going to be different than if you got 4th place. So this would be a permutation. And you know you can make a systematic list, let's say, to get the answer to this. You create a 5-digit password from 9 possible digits, and these digits cannot repeat. That would be a permutation because order matters. If you had a password that was, let's say, I don't know, COUNT, count, that would be a different password than if you did, let's say, the reverse of that. So order matters, so we would use permutations here. Let's say you're buying DVDs. Well, it doesn't matter if you pick, let's say, Monsters, Inc. 1st or 6th. It's just you're either buying it or you're not. So this would be a combination. Order does not matter. If you rank your 3 favorite foods from the 10 meals you've eaten, that element of ranking alludes to order. So just like there's order when you write your password or placing in a race, if you're ranking your meals, you could say lobster is your favorite meal, or you could say it's your 2nd favorite meal, and those 2 lists or options would be different. So that would be a permutation because order does in fact matter. All right, nice job on probability. Go team.